Next, we're going to look at the stability of various resonance structures. Not all resonance structures will be equally significant. You might have a compound that has many valid resonance structures, and none of them violate any of the rules that we learned, but it could be possible that one of them is insignificant or less significant. And so we want to always be able to identify what the best resonance structure is. And that's because the best resonance structure, the most significant one, is the one that the resonance hybrid will most resemble overall. Next, we're going to look at different ways that we actually assess the stability of the resonance structures or the resonance contributors. The first is formal charge. So formal charge will generally decrease the stability, especially if you have a resonance structure that places a positive formal charge on an electronegative atom or a negative formal charge on a more electropositive atom. Second thing we'll look for are complete octets. Having a complete octet increases the stability of that resonance structure or resonance contributor. So if you have atoms that do not have complete octets, but it's following all the rules for resonance structures and following the bonding patterns, it doesn't mean that it's not one of the contributors. It's just not a major contributor, or it's not a stable resonance contributor. Let's start by looking at a simple molecule, acetic acid, and we'll draw some resonance structures for this molecule and then analyze them to figure out what would be the best resonance structure or the major contributor. Those two things mean the same thing. So we can see in our neutral molecule of acetic acid, we don't have any formal charges in this first structure that we're given. So we would know that on the top oxygen, what's not being shown, 2 lone pairs of electrons, and on the bottom oxygen, 2 lone pairs of electrons. Each of those oxygens is neutral and it has 2 bonds to it, whether it's 1 double bond like the top or 2 single bonds like the bottom. So from there, I can see a couple patterns that we could use. We could take the pi electrons that are in between the carbon and the oxygen that's double bonded, and we could move those pi electrons up to the top oxygen. So if we take these electrons right here and we start and we push them up here, that would be separating the charges there. So our structure then would be we would have 3 lone pairs on our oxygen, negative formal charge. We now have a carbocation, an electron deficient carbon, so we would have separated that charge there. The other thing that we could do, the third resonance structure, is if you look back at the first one, it's a little bit easier to see. You have a lone pair of electrons, allylic to a double bond. So we can move that lone pair of electrons towards the double bond, or if we want to start with the second structure, towards the carbocation. Because it's a carbocation and it does not have a complete octet, it can accept those lone pair of electrons. So we would take our electrons and we'd push them in between carbon and oxygen. We're going to draw our resonance arrow and our last structure. So now that we pushed those electrons on the right oxygen in between the carbocation and the oxygen, we have a double bond there. And our carbon now does not have any charge on it because it was a carbocation, but now it has 4 bonds. So we have a 0 formal charge on that carbon. But what about our oxygen on the right-hand side? We had 2 lone pairs. Now we're left with 1 lone pair, and we have 3 bonds to it, 1 double and 1 single. So we're going to have a positive oxygen. So notice in each of our 2 resonance structures, we have a plus and a minus. We have a plus and a minus because those add together to be neutral. So we have no charges overall in this molecule. So next, let's assess the stability of these 3 resonance contributors. In our first one, we have 0 formal charge. And that's good. We minimize the amount of formal charge, and everyone has an octet around it. In the middle resonance structure, we have a negative 1 charge on oxygen and a positive 1 charge on carbon. Carbon does not have an octet. On the right structure, we have a -1 formal charge on the upper oxygen and a +1 formal charge on the right-hand oxygen. In this example, everyone has an octet. Now, our best structure is going to be the first one because we have no formal charge, we've minimized it, and everyone has an octet, so everyone's happy. Comparing structure 2 and structure 3, there's a little bit of a discrepancy here because according to electronegativity, the third structure would be worse because we've placed a formal charge, a positive formal charge, on oxygen, which is electronegative. Oxygen's highly electronegative, more electronegative than carbon. So if we had to choose between electronegativity, I would prefer having a +1 charge on carbon rather than having a +1 charge on oxygen because it's less electronegative. But in the middle structure, carbon doesn't have an octet, and on the right structure, everyone does have an octet. Usually, the general rule of thumb is having an octet is more important than dealing with electronegativity. So in this case, everyone having an octet is going to be the major factor that makes this one the middle range resonance structure. It's okay. It's not as good as the best resonance structure, but it's an okay resonance structure and it will still contribute to the overall resonance hybrid picture. The middle resonance structure is okay as well. It's a little bit less okay than the one on the right. We still do have a charge separation. Carbon does not have an octet. So that's what pushes that one down just a little bit lower than the structure on the right. But because we only have 2 charges, 2 formal charges, and not like 3 or more, it's still an okay resonance structure to draw. So all 3 of these would contribute to the overall structure of acetic acid. Now let's do the same thing that we did for acetic acid, but look at the acetate ion. So this is an ion. Acetate, if you remember, is C2H3O2-. This has a -1 charge. So in each of our resonance structures, there is either going to be an atom that has a -1 formal charge, or all of the formal charges will sum to -1. The formal charges should always sum to the charge on the ion, or if it's a neutral molecule, they should sum to 0. So starting with the given structure for acetate, we have what's not being shown, 2 lone pairs on the top oxygen, and our right side oxygen has a -1 formal charge, so it has 3 lone pairs not being shown. Any one of those lone pairs we could say is allylic to our double bond between our carbon and our oxygen. So that's one of our bonding patterns. We can push one of the lone pairs in between there, and then when we do that, we have to use 2 curvy arrows, so the pi electrons in between the carbon and the oxygen will have to move up to the oxygen so that this carbon does not exceed an octet. So let's draw our next structure here. We now have our top oxygen with 3 lone pairs of electrons on it, so it's going to have a -1 formal charge. Our electrons off of our right-hand oxygen moved as a double bond in between this carbon right here and our oxygen. So there are going to be 2 lone pairs left on that oxygen. So this would be one of our resonance structures, and it basically looks the same as the first one, only now our negative formal charge is on the other oxygen. And so both of these resonance structures are equally good. Everyone has an octet. No one is electron deficient. There is no electropositive atoms that are bearing a negative charge or vice versa. There's one other structure that we could draw from here that might or might not be important. So we could take the pi electrons in between carbon and oxygen, and we could split those and separate the charge. So if we take these pi electrons and we push them up to this oxygen, Then that would give us our third and final resonance structure. We would have our top oxygen, which still has a negative formal charge, and this oxygen, which started with 2 lone pairs, and then we moved those pi electrons, and there's that third lone pair there. And so now that oxygen also has a -1 formal charge, and our carbon is left electron deficient and only has 6 electrons around it. So now we're going to have a +1 formal charge on our carbon here. And so notice we have -1, -1, and +1. The sum of all the formal charges on this last resonance structure adds up still to -1, which is the same as the charge on the acetate ion. So when we're looking at these structures, the first two, they are going to be our best resonance structures, and they're equally as good as one another. They both have a negative formal charge on an oxygen, and the octet rule is satisfied. This resonance structure right here that has 3 formal charges on it, that's bad. That's too many formal charges to have when we separated those charges. So this third resonance structure is not significant. It doesn't really contribute to the overall resonance hybrid, and we really wouldn't even have to draw it or consider it when thinking about how the resonance structures would impact a reaction mechanism. And that is due to having those 3 formal charges on there. More than 2 is usually considered to be bad. As was said before, the octet rule is usually a bigger factor than formal charge when determining the stability of your resonance structures or when deciding what one is the best one. So let's look at these 2 examples and draw the resonance structures and decide what one is going to be the major contributor, or in other words, the best structure. So in our first one, we have a carbocation, so that carbon does not have a complete octet, and there's 2 lone pairs of electrons on the oxygen. Because carbon doesn't have an octet, we can take one of those lone pairs of electrons and move them as a double bond in between oxygen and carbon. That will give us a resonance structure where we have oxygen double bonded to carbon, and we have our 2 methyl groups coming off. We still have our hydrogen here. There is 1 lone pair of electrons on the oxygen atom now, not 2. And so before, our carbon bared the positive charge. We started with a positive charge. That means we have to have a positive charge in our resonance structure that we draw as well. But now that positive charge is going to be on the oxygen atom. So when looking at the 2 of these, the second one has the oxygen with the +1 formal charge, which you would think that you would rather have that +1 formal charge on carbon, since carbon is less electronegative than oxygen. But in the second structure, everyone has an octet. And that's going to be the major factor that makes the right-hand structure the best resonance structure, or the major contributor. Looking at the one below, we have nitrogen with 4 bonds, and so it has a +1 formal charge. The only thing that we can do to draw a resonance structure here is to take the pi electrons in between carbon and nitrogen and move them to the more electronegative atom, which is nitrogen in this case. So we're going to take these pi electrons and we're going to push them to the nitrogen. And so then in our resonance structure, we're going to have nitrogen with 3 single bonds and a lone pair of electrons on it. So now that nitrogen, which is trivalent, does not have any formal charge. But when we remove those pi electrons, the carbon atom is lacking something now. It had 4 bonds to it, but now it only has 3 bonds to it. So now that carbon atom is going to have a positive formal charge on it, and it has an incomplete octet. So even though in the right-hand structure, carbon is bearing the positive formal charge, and in the left-hand structure, nitrogen is bearing the formal charge, the major resonance structure, the best structure, is the one on the left with nitrogen with the +1 formal charge. And that's because the same reason as at the top, everyone has an octet in that structure, and that's a bigger factor than formal charge overall. So our best one is the one on the left-hand side, even though the more electronegative atom has the formal charge. So just to kind of wrap up here, we're going to review what delocalized versus localized electrons are, because really that's what resonance is. Localized electrons are electrons that are not in resonance and cannot participate in resonance, because essentially you can think about them like being stuck on the atom that they're on. They have no way to move throughout and participate in resonance. Delocalized electrons are electrons that are in resonance or can participate in resonance. They are not stuck on a specific atom. When you have delocalized electrons on a molecule and they can move throughout, that increases the stability of the molecule. When we see that electrons are going to be delocalized, we can look for molecules that have a string of atoms that have an unhybridized p orbital. So electrons must be able to exist in an unhybridized p orbital that overlaps with other unhybridized p orbitals on the atoms that neighbor it. If that occurs, then those electrons can move throughout those atoms and participate in resonance. They can be delocalized. So electrons must be on an sp2 or sp hybridized atom, not an sp3. If it's sp3 hybridized, there is no leftover unhybridized p orbital. But if you have an sp hybridized atom, then there's two leftover unhybridized p orbitals that didn't go into the hybridization mix. And if you have an sp2 hybridized atom, there's one unhybridized p orbital that did not get thrown into the mix. Let's look at an example. Does the delocalization of the electrons in the amide, and remember amide is just the name of a functional group, create a more or less stable resonance contributor? So in order to draw the resonance structure, we would take the allylic electrons that are on the nitrogen and push them as a double bond in between the nitrogen and this carbon. And then with the second curvy arrow, we would push the pi electrons in between carbon and oxygen up to the oxygen as to not exceed an octet on the carbon. So this is one of our patterns of resonance that we saw before, where we needed two curvy arrows. And our structure that we would end up with is an oxygen with a -1 formal charge and the nitrogen with a +1 formal charge. So essentially we started with a molecule that had no formal charges, and we created one that does have some. So right away, we can see that everyone has an octet in both structures. So the only thing we really have to do is assess the formal charges. Minimum formal charges is better than having them. So our best structure is going to be the one on the left. So it created, to answer the question, a less stable resonance contributor when we delocalized the electrons of the amide. But overall, these are still two resonance structures that will be important when assessing something like an amide functional group. When looking at electrons that can be delocalized versus ones that are stuck or localized, it's really interesting because if we look at our amide molecule that we saw on the previous slide, sometimes atoms that you would think are going to be sp3 hybridized will actually become sp2 hybridized just so they can participate in resonance. So if we look at an amide, which remember an amide functional group is where you have a carbonyl next to a nitrogen. So we have that carbon-oxygen double bond, which is bonded to a nitrogen atom. If we look at our nitrogen and figure out what the hybridization is there, this would be considered AX3E. We have 3 bonding sites around that nitrogen and 1 lone pair. And so normally we would say this is trigonal pyramidal. And the hybridization of something like this we would know is sp3. But if that nitrogen was really sp3 hybridized, then those electrons on that nitrogen could not participate in resonance because there would be no unhybridized p orbital for them to reside in. So in the case of this, that's not what's really going on. What's really going on is those electrons are resonating through the molecule, and we have a picture like the one we drew on the previous slide, where there's a double bond in between our nitrogen and our carbon. And when we look at nitrogen like this, it's going to have a positive formal charge. Now looking at our nitrogen, it has three things around it and no lone pairs. It's AX3, which is trigonal planar. And the hybridization for trigonal planar is not sp3, but sp2. And when we have sp2 hybridization, we're left with one unhybridized p orbital. And that is where those lone pair of electrons on nitrogen must live. If they are going to participate in resonance, they must be in an unhybridized p orbital. So if that nitrogen atom actually were sp3 hybridized, then those electrons couldn't even participate in resonance. So it takes a little bit of time to just become familiar with some of this stuff, and understanding some of these patterns of resonance that we've previously gone through will really help with knowing when electrons are localized versus delocalized. So those electrons on that nitrogen are delocalized, and they really do live in an unhybridized p orbital. The picture on the right-hand side shows those three unhybridized p orbitals, which are the dumbbell-shaped ones, one on nitrogen, one on carbon, and one on oxygen, all on adjacent atoms overlapping one another, which allows those electrons to participate in resonance between the nitrogen, carbon, and oxygen. So all three of those atoms must have at least one unhybridized p orbital that can overlap and allow those electrons to move throughout. Understanding what orbitals electrons live in, whether they're hybrid or unhybridized atomic orbitals, is important, especially when we start learning about aromatic compounds later. So for example, we generally saw that when you have a set of electrons or a lone pair that is allylic to a carbon-carbon or a carbon-oxygen double bond, a double bond of some kind, that they can participate in resonance. So if we look at the molecule on the right, which is called pyridine, this is an organic base, you'll notice that you have a lone pair of electrons on the nitrogen, and they are allylic to this pi bond that's in the ring. So it would be tempting to think that we could take those lone pair of electrons on nitrogen, say that they are living in an unhybridized p orbital, and push them over in between the carbon and the nitrogen. And then we would use our second curvy arrow to move the pi electrons in between carbon and carbon over to this carbon atom right here. But in reality, we cannot do that. That's actually not a valid resonance structure. And it has to do with these electrons on this nitrogen being very different than the electrons that were on the nitrogen of the amide. That amide nitrogen was sp2 hybridized, and those electrons could occupy an unhybridized p orbital. In this example, and this is something that we'll come back to later in the semester or even next semester more in depth, that cannot happen with these electrons because these electrons are actually localized and they cannot participate in resonance. So this would not actually be a valid resonance structure. We couldn't even draw that. And it's interesting because it looks like we didn't break any of the rules. We're not violating the octet rule on anything. So why can they not move around? Why can they not be delocalized? And the answer comes down to what orbital they must be living in. When you have an aromatic compound, such as that ring that's involved in pyridine, the unhybridized p orbitals are actually already overlapping to make that ring structure. So the lone pair of electrons that is on the nitrogen atom cannot reside in an unhybridized p orbital, and it must be living in a hybrid sp2 orbital. And so since that lone pair of electrons is in an sp2 orbital, then it cannot be in an unhybridized p orbital, and it cannot participate in resonance. And those p orbitals on the nitrogen right here, that unhybridized p orbital, is being used to create an aromatic compound to overlap with the carbon atoms of the ring. And so this is something that's really important when we learn about aromatic compounds more in depth, and we decide if they can possess a special property known as aromaticity, which gives them extra stability. But in this example, I just wanted to point out to you that on our nitrogen atom, even though it does have an unhybridized p orbital and it is in fact sp2 hybridized, that lone pair does not live there. So since the lone pair is not in that unhybridized p orbital, it cannot participate in resonance, and therefore we cannot push those electrons, those lone pair of electrons on the nitrogen throughout the ring. So there are a lot of intricacies and special rules and then things that violate those rules and stuff you have to practice and kind of develop over time to really understand resonance very in depth. Here is a structure of an amine functional group. So it's not an amide, it's an amine because we don't have nitrogen next to that carbonyl, which is a carbon double bonded to oxygen. And those lone pair of electrons on an amine are another example of localized electrons. Those are not going to be participating in resonance at all. And so amines are really strong organic bases, and they're strong because those electrons are localized. So localized electrons are less stable, which less stable means more reactive. And so when this reacts with something that can function as an acid, those electrons can be donated from the amine, which amines are just derivatives of ammonia, to pick up a proton or react with something else that is acidic. And so that's what makes these rather strong bases and highly reactive, is due to them having localized electrons.